Professor Yuan is a chair professor and a global STM professor at the City University of Hong Kong. He is a fellow of Australia Academy of Technology and Engineering and a distinguished fellow of IWA. He is also editor-in-chief of Water Research X, and his research focus on development of innovative solutions for urban water management through effective integration of fundamental science and applied engineering. Okay, so Professor Yuan, please, floor is yours.
Thank you very much, Bingjie, for your invitation and for your kind introduction. I just like to check, and can you see my screen? I have now shared my screen. Yeah. Excellent. Thank you. And good morning, good afternoon, everybody. My talk today is generally in the area of net zero carbon wastewater management. My direct focus is on greenhouse gas emissions from urban water systems. That is a critical component element in the net zero goals. Now, in terms of achieving the goal, I think we have to define what we mean by net zero. So net zero really means the carbon emitted from the system is equal to the carbon sequestered by the system. And if that is not, if we don't achieve that balance, and the utilities may have to buy some carbon credit in order to achieve net zero goal. And urban water systems emit greenhouse gases. There are three scopes there. Scope 1 is a direct emission. That basically the greenhouse gases directly emitted by the system itself. Scope 2 is power consumption, CO2 emission due to electricity consumption. And obviously that emission is dependent on the power mix, the mix of your electricity grid. And Scope 3 are related to the upstream and downstream processes. So the emissions upstream of urban water systems and downstream of urban water systems. For example, your customers using the emissions associated with that use. That's the downstream emission. But in terms of the carbon emissions from the water utilities, really we just talk about Scope 1 and Scope 3. So if we say net zero, the boundaries are around Scope 1 and Scope 2. Sorry, did I say Scope 3? I think that was an error. So Scope 1, Scope 2 are counted against emissions from the urban utilities when you look at your goal of net zero. Although I have to highlight, there are actually a lot of opportunities for urban utilities to contribute to the reduction in greenhouse gas emissions in Scope 3, and that, in my opinion, that should be a credit you earn if you help your customers to reduce emissions. In terms of emissions, strategies to reduce emissions, really for Scope 1, we just need to reduce the emission. And for Scope 2, there are a few options. One is we reduce energy consumption, then we reduce Scope 2. And the other one is you recover energy and use that energy for the treatment process. And then in that way, you reduce energy consumption, then you reduce your Scope 2. And then if you use renewable energy, and that will also reduce your emissions to emission. Oh, something's wrong here. Sorry. Okay. And then you can generate another strategy is to generate offsets by, for example, by planting trees, etc. Now, talking about Scope 1, direct emissions, we really talk about the three gases that are emitted by wastewater system or urban water system. Nitrous oxide, N2O, we all know that's a potent greenhouse gas. Methane is also quite powerful greenhouse gas emitted. The third one is actually CO2. CO2, in terms of CO2, there are two different sources. One is this biogenic CO2, and that is not considered as your emission. The other one is for the chemical, customers use chemicals, for example, in their household activities. And some of those chemicals are produced from fossil carbon, and then if you oxidize that to CO2, and that CO2 is emitted, and that is your direct emission. So three types of fugitive direct emissions. So they're called fugitive emissions. Now, urban water system, if we talk about the urban water system as a whole, there are so many elements there, and they all emit greenhouse gases, direct emissions I'm talking about. But the key ones are actually the sewer networks, which emit methane, that is confirmed, and also emit some N2O, but that's not very much. In general, it's a small emission. So my opinion is that is indeed negligible. But then we have the wastewater treatment process, including the sludge treatment process. And there, that's probably the biggest direct emission, biggest sources for direct emission. So my talk today will be focused on N2O emissions in wastewater treatment plants, methane emissions in wastewater treatment plants, fossil CO2 in wastewater treatment plants, and methane emissions from sewer networks. So those four topics today. In terms of N2O emissions, and we have a reasonable understanding how N2O is produced in a wastewater treatment process. So everybody knows about biological nitrogen removal. That includes nitrification, basically ammonia to nitrite and to nitrate, and denitrification, which is basically a nitrite converted to nitrogen gas. There are multiple processes that contribute to N2O. For denitrification, N2O is actually sitting in the pathway. So basically all nitrogen removed through denitrification will have to go through N2O, so that there is a heterotrophic denitrification pathway. And then we also know that ammonium oxidation, the AOB, ammonia oxidizing bacteria, they have a pathway to do denitrification, but they do incomplete denitrification and producing N2O as the end product. That's called AOB denitrification. And then we also have AOB hydrosillamine oxidation pathway. Basically, there's any issues there? If not, I continue. So N2O can be produced and leaked as a byproduct of ammonia oxidation. So first question, where is N2O emitted? And is mainly emitted from aerobic zones, and with the N2O emission from anoxic zones typically small. This is not because more is produced in aerobic zones. This is because in aerobic zones, you have aeration, which provides stripping force for N2O. So anything produced there, majority of the N2O produced aerobic zones is stripped, causing the emission. Obviously, in the denitrification in the anoxic zone, a lot of N2O is produced because N2O is a necessary intermediate for denitrification. But the driving force for the emission is small. So the only surface emission, and giving rise to relatively small N2O emission from anoxic zones. However, if you have N2O accumulation in an anoxic zone, and that is carried over to aerobic zone, and that can be stripped there. So denitrification in that case can contribute significantly. And by whom? So heterotrophic bacteria produce a lot of N2O, but if they produce N2O in the anoxic zone, that does not necessarily lead to emission. And on the other hand, in comparison, AOB, they produce N2O aerobically. That means when they produce N2O, there is a driving force for that N2O to be stripped. So that means N2O, AOB actually are the main dominating force. For I'm sorry, I have to cough here. Apologize, I got a bit sick. So N2O will be the dominating organisms for N2O production. And oh, I really struggle with my throat. Apologies again. I hope it will work out okay from now on. So next question is how much? How much is N2O produced? And then there are many different ways to quantify the N2O emission. One is we measure gas phase directly. We measure the concentration, flow rate. Then we come up with the flux, and then that's based on Hoot method. And then the other method is based on calculations. That's the mass transfer utilizing mass transfer equations. Okay, so in terms of how much, so there are a lot of results reported in literature, and I'm summarizing some of the results. The first set of results was obtained by our own group more than 10 years ago, probably 10, 15 years ago. We measured 7 wastewater treatment plants in Australia. Before I present the results, I like to define emission factor, because there are so many different definitions of emission factors. So the one I'm using now is the emission factor based on influent nitrogen. So percentage of influent nitrogen converted to N2O. It's just, we need to bear that in mind. That's my definition for this talk. And the rule of thumb, so how big is big is big. So basically, if 0.5% of the influent COD is converted to N2O, and roughly speaking, for a typical wastewater treatment process, that adds roughly 20% of your carbon footprint. So 0.5 more or less equivalent to 20% of your carbon footprint. So that's really significant now. These are the results from the 7 treatment plants we monitored more than a decade ago. And you can see it really varied in very large ranges. So the lowest we got was below 0.2%, and the highest we got was 1.15%. And in fact, in one period of one monitoring period, when one of the treatment lines was taking offline, and then the emission factor of the remaining lines increased quite significantly because the loading was increased. In general, the median level is around 1%, 0.91%. That's the median level. These are the results of our own measurement campaign. And then these are the results from even earlier studies done by Kartik in the US. They measured N2O from 13, I believe, treatment plants. The N2O was in the range of 0.01 to 1.8%, with a median 0.4%. I think later on, my observation was that some of those probably were underestimated, quantified some of the emissions. So the median level is likely higher than 0.4. That's my personal observation, which need to be verified. That's the US results. European results, very similar. You can see the 7, I think there's a 7 plants, so range from 0.01 to 2%. Average, this is not median, this is average 0.9. So you can see very, very similar results. So the common features include large variation, so a lot of variation between plants. And also there are a lot of variations even within the same plant. And then the median level is roughly just below 1%. Then in the IPCC 2019 report, they pulled together some data from the literature, and then they made this graph. So the vertical axis is the emission, basically kilogram N2O per day and the horizontal axis is the TN loading, kilogram M per day. Then you do the regression, you get this slope is 0.6%. So the recommendation by the IPCC, the emission factor recommended by IPCC is 1.6%, which is substantially higher than 32% higher than their initial recommendation. Unfortunately, later researchers found that there were some errors in the IPCC calculations. With all the errors in data corrected, and then this is the emission factor about 1.1%, so lower than 1.6. So this data sort of agree with quite well with the three data sets I just presented to you. Okay, those, so let's say roughly 1% on average, 1% of the nitrogen and added to treated by the wastewater treatment plant is converted to N2O. That helps. So the data help us to quantify, but does not really help us to reduce. So we want to reduce, mitigate N2O emissions. So this, so researchers have done some correlation analysis to see what is the driving factor to reduce, what could be the driving factor to reduce N2O emissions. So this graph is quite interesting, generated based on two sets of data. This is the European data. So the blue is the European data, and the brown color is Australian data. So although the data they are separated, but nevertheless the trend is relatively similar. The vertical axis is the emission factor, and the horizontal axis is the total nitrogen removal efficiency of your treatment plant. So 90% means 90% of our nitrogen is removed. And what you can see here is when you have a wastewater treatment plant that has a good nitrogen removal performance over 80–90%, the N2O emission is lower, that's very good news. That means if you optimize your treatment process to achieve better TN removal, in the same time, you would also be reducing N2O emission. So that's very, I think that's a lucky news there. And then in terms of mitigating, directly reducing N2O emissions by optimizing operation, deliberately optimizing the operation based on what we know, based on the mechanisms we know about N2O production. And our group did one of those early studies where we optimized the aeration in the treatment process, and that was a pretty powerful. So we reduced, in our study, we reduced N2O emission by 35%. And in the meantime, we reduced energy consumption by 20%. So this is another good news. So it does not mean if you, basically to reduce N2O emission, it does not necessarily increase your energy consumption. In fact, by reducing N2O emissions, by controlling aeration more appropriately, we can reduce energy consumption. Therefore, we also reduce the scope 2 emission, which is really a very good news. Now, this N2O summary of N2O emission from wastewater treatment plants. So mainly from aerobic zones, and mainly by AOB, ammonium oxidizing bacteria, emission factor probably around 1.1%, and that's before an optimization is done. But we can reduce emission by controlling the treatment plant to achieve better TN removal. As I said, that's a very good news. I would say we have got quite some understanding of N2O production mechanisms. It's also fair to say we don't know every details there. So we still have room for scientific research in that space. And N2O can be mitigated by relatively easily. And then you can achieve energy saving in the meantime. So that's the summary of N2O emission. Now, coming to the next topic, methane emission from wastewater treatment plant. There are a number of sources. One is from influent. The wastewater coming to the treatment plant has some dissolved methane generated in the sewer networks, and that will be emitted because once it reaches the aeration basin, that will be stripped. And part of that will be oxidized, but majority will be stripped. So that's one source. Another source is biogas leakage. And so you got produce biogas that has methane, you have to manage it well. I think that's more a management issue to minimize the leakage. Another one, which is a technological issue. So we use anaerobic digestion, digesting sludge, or directly digesting wastewater, the raw wastewater, and then produce methane. In that way, we recover carbon. We recover energy from organic carbon as biogas. But then the effluent of the anaerobic process has dissolved methane, and that if that is not removed appropriately and is stripped into an atmosphere, and that will add dramatically a lot of greenhouse gases to your carbon footprint. But the good news is some technologies have been developed to reduce that emission. And one of those, this is developed by our own group. We use MABR, membrane air-rich bioreactor. And basically, I won't go into details. Basically, we use the anaerobic effluent, and we use that to support denatrification. So we achieve two goals with one process: reduce methane emission on the one hand, on the other hand, we enhance nitrogen removal by enhancing denatrification. So for those who are interested in this process, you can have a look of the reference I cite here. And another one, another source of methane is in your sludge sludge treatment. So in Australia, there are a lot of sludge drying lagoons for storage, for storing sludge, and for drying sludge, reducing sludge, and that can be a significant source of methane. And here is a really high-level summary of what may happen in a sludge drying lagoon. So that's a sludge drying lagoon there. You can see multiple cells there. And what we found was methane emission can be substantial from such cells. Again, no time for details. You can read the paper we published, but that can be a significant source of methane. And now, the last part of the emission from treatment plant itself is the fossil carbon emission from treatment plant. The carbon in wastewater, as I said, majority of the carbon in wastewater has the biogenic sources. Basically, they are from food, from plants, and therefore, when we convert that into CO2, that's not regarded as direct emission because of the short cycle of carbon. However, if for the carbon in wastewater that has a fossil origin, and then if that is converted to CO2, that will give you a direct emission. But the fossil carbon, in terms of the isotopes, C13, C14, they are depleted in 13, C14. So that means by measuring C14, C13 fractions, we are able to differentiate the biogenic carbon and fossil carbon. We indeed did that for a number of treatment plants. I think 4 treatment plants. So here the treatment plant, and then we measured at multiple points. So the influent, the gas phases, and then the effluent, then the sludge, and something in between. So we measured the inlet, so incoming stream and outgoing streams, both gas, liquid, and solids, and then we tried to look at the carbon balance. And then by doing that, we came to the observation that CO2 emission, the emission of fossil carbon, CO2 from a treatment plant, it's relatively a small part of your total emission, about 1 to 7%, depending on the sources of your wastewater. So again, there's a paper there for people to read. Now I'm coming to the last part of my presentation, which is the methane emission from sewers. And as I said, N2O emission from sewer networks is relatively small, so we can probably quite safely ignore that emission. But methane is a different case. In the 2006 IPCC report, there was claimed that sewer methane is negligible, so we don't need to worry. But in the 2019 report, this sewer emission was recognized, but the emission factor was not corrected. And here are the results. We reported in 2008. I think we were among the first to report methane emissions from sewer networks. So this is one pipe. There's another pipe, and when you see a few milligram per liter of dissolved methane, and that's quite a bit. That's quite a bit. Then we measured a network. This is the previous slide. We had two pipes. Here we had a network. So we put a dissolved methane sensor at the end of the network. So everything produced in the network was captured there. And this network is about 3 megaliter per day with average HRT of 9 hours, which is quite long. And then, no surprise, we got a fair bit of methane emissions, so 10 milligram per liter, and that's a lot. And here, it's the winter, lower temperature, lower production, but there's still 7 milligram per liter. So it's quite a bit of methane formed. And then this was also confirmed in the gas phase measurement. And so you can see in this particular case, methane concentration was about 2% of the gas phase, and 5% is already reaching the explosive range. So this is 2% is quite high. Now, how much is much? And so based on what our observation, if we assume the network produces methane at 2 to 20 milligram methane per liter, 20 is really very, very high, the higher end. And I think 1 to 2, you will always produce some. So let's say 2 to 20. How much is that? And if we convert that to CO2 equivalent, that's 0.1 to 0.4 tons of CO2 per megaliter of wastewater. And then if we look at typical CO2 emissions from a wastewater treatment plant, 1 to 1.5 tons of CO2 per megaliter of water. So that means the methane emissions would contribute 3 to 40%. So from relatively a small contribution to a substantial contribution. That's the rough range. But then it really, for a specific network, this is a sewer network in DC, in Washington, DC. For a specific network, you want to know how much that is that network is emitting methane, and then we really have to do something specific for this network. But measuring methane emissions from a network is an impossible task, because methane is produced everywhere and methane is emitted everywhere through the water-air interface, through manholes, pumping stations, and so on. And it's impossible to measure the methane flux across a network. So modeling becomes an important tool for quantifying that emission. But even constructing models for large networks, like a network for entire city, that's a very, very big task. And it's very difficult to do, will be very costly. So what we have tried to do was to come up with accounting equations to help IT, basically to help IPCC to develop this emission factor calculations. So what we did, we built mechanism models into one of the sewer network models. That's our own model, SUEX. And then we use the data we collected, we calibrate the model, and then we use that model to produce a lot of data. So we produce a lot of data, and then we use that data to support the development of accounting equations. So basically, that's some sort of machine learning from data. That's the methodology. And this is what we have come up with. For gravity sewers, we got a very simple equation to estimate methane emissions based on flow rate, based on diameter, and based on the slope. These are the parameters we have determined. For rising mass, and that's the equation, it's even simpler. It's only diameter plus a parameter. So we calibrate the parameters. With that, to estimate methane from a sewer network, it becomes a very easy task. Excel worksheet, and then you just apply these equations, and then you can estimate how much methane you emit. My conclusions of my emissions, I would say knowledge related to NO2 and methane emissions from urban water systems was enhanced substantially in the past decade. And the second, N2O and methane emissions can contribute substantially to the carbon footprint of urban water system. In the future, the contribution, the relative contribution will increase when we use more and more renewable energy to power the treatment process. Mitigation is possible. That's good news. Now we do have the knowledge and the models and etc. to help us to mitigate. If we really want to achieve net zero, I believe some sort of offset will be needed. Okay, I think that's. I'm finishing my presentation. This is over years. So many people in my group were involved in those studies I reported to you. I acknowledge their contributions. You can see Bingjie, that's Bingjie, maybe 10, 15 years ago. Thank you very much.